Am I audible, student? Rohit?
Yes, sir.
Okay, thank you. So in the last class, basically we were discussing about this reset windup or integral windup, and there we have taken this example system to understand. It is a heat exchanger example, and this is the graphical representation of the operation of that heat exchanger. This also we have discussed. Then I have given this table to you. Okay. And based on this data, we have noted our observations till this point. We have noted our observation yesterday till this point. Now, I also mentioned that to tackle this, particularly the effect of integral windup, we need anti-reset windup. Okay, I indicated in the last class that to reduce the effect of integral windup or reset windup, we need to devise a anti-reset windup. We need to devise an anti-reset windup. Now, what is the fundamental concept behind this anti-reset windup? You can note down these points. So I think it's not difficult to understand. Integrator needs to be updated through back calculation. For developing the anti-reset window, we take care of these issues. First one is integrator needs to be updated through back calculation. And second one is stored error integer value is recomputed so that the controller output is exactly at the saturation limit. So that the controller output is exactly at the saturation limit. So these are the two major issues which we actually take care of. And if you come to I equal to 4, then you can easily understand. Let us come to I equal to 4. This is I equal to 4, you see. At I equal to 4, our error is 20. And error integer is 30 plus 20, that is 50. So our calculated C or manipulated variable is 50 plus 20, 70 plus CS. So it is coming 120. But since valve opening is 100%, maximum valve opening permitted, that is 100%. So we cannot implement 120% valve opening. So we can maximum 100% valve opening. Okay. So although it is calculated 120, it is implemented as 100. So 20 is extra, that is calculated here in our computer program. So what is suggested in anti-reset window, you also make this 100 through back calculation. How we can do it? Just you consider here 30. You change this error integer value 30. Then 30 plus 20, that is 50 plus CS 50, it is also coming as 100. So this is the concept of anti-reset window. Fine. I hope you understood this. Like if you come to this point, it is 15 error. So it is coming 130. So to make it 100, we need to consider here how much? 35. Through back calculation, we can change 65 to 35 in our computer program. Then it becomes also 100 because 35 plus 15, that is 50 plus CS. So it is coming also 100. So this is all about anti-reset windup, and I'm not going to complicate it again because the structure is also there, some explanation is also there. Now next let us come to our third controller, that is PID controller, proportional integral derivative controller. We have started so far proportional only. Then we have started PI, that is proportional integral. And our final control structure is PID, proportional integral derivative controller. It is basically the combination of three actions: proportional action, integral action, and derivative action. The block diagram is also shown in the right hand side, you see. To each action, error signal is the input, and the output, all three outputs are getting added, and finally we are getting the controller output in terms of C. I repeat, for all three control actions, error is the input, and from all of them we get output, and those three outputs are getting added here, and that yields controller output C. This is a controller equation, you see. So till this point, PI we have started. One additional term is added here that represents the derivative action. Proportional action, mathematical representation of integral action. So till this point we have started in PI controller. Now for PID controller, this additional term is added that represents derivative action. So this is the combination of three control actions. So one additional term is there, you see, that is tau d. All terms are known in this equation, in fact discussed before. One new term appears in this PID controller equation, that is tau d. And this tau d is derivative time constant. Tau d is called derivative time constant, and its unit is time. Student, can you derive now, or can you find out what is the transfer function of this PID controller? Let me know. Find the transfer function of PID controller and let me know what is that.
Sir, it is Kc into 1 plus 1 by tau s plus tau ds.
Correct. What's your roll number?
19CH 30008.
Good. Anyone else got? Gandhi Bhagavati 30006. Are you there? Got transfer function? You are not audible. You just, yeah, tell yes or no. Oh, it's not coming. Anyway, you try for this. Roll number 30025, Somil Bharilya. Somil 30025. 35, Vaishnavi. 30035, Vaishnavi. Vatsal, you got 37, 30037. Vatsal. Okay. So this is the transfer function you see. You can match with your result. Now, you know, I have made several remarks, observations on proportional and PI controller. Now I am directly asking to you, can you make any remark on PID controller in the similar line we did for P or PI controller, student? Do you have any remark on PID controller in the similar line we made some observations for P or PI? Anyone? Open to you now. Any remark? Anyone? No. Okay. Let me make then couple of remarks. Yeah, first remark is what happens on epsilon equal to constant? If epsilon is a constant value, what happens to derivative action? Anyone can give the answer?
It becomes 0.
Sir, it will be 0.
Yes, it will be 0. So when this error term becomes constant, there is no response we get from derivative action. So this is our first remark. If this error signal becomes constant, there is no response we get from derivative action. Yeah, now we want to discuss another important term that is called derivative kick. In the second remark, we want to discuss another issue that is popularly called as derivative kick. Okay. Now suppose this error is like a vertical line. Carefully listen. Suppose error is a vertical line, like we observe in case of step change. We consider a vertical change first, then a horizontal continuous change. My question is, in that vertical change of error signal, what happens to the derivative action? Got the question? If we introduce a step change in error signal, that means there is a vertical line followed by horizontal line. My question is, during that vertical change, what happens in the derivative action? How it responds?
Sir,
Yes,
it will tend to infinity.
correct. What's your number?
19CH 30034.
So let us discuss this mathematically for this derivative action. You see, we are considering only the derivative part. We are not considering the proportional or integral action. Okay. In this discussion, we are considering only the derivative action. We are not considering proportional and integral action. So equation 9 basically represents the derivative controller or derivative action. Let us take Laplace transform. Then we have this equation 10. Now, as I told, we want to introduce a unit step change in error signal. We want to introduce a unit step change in error signal. That means epsilon bar equal to 1 by s. Then equation 10 gets this form, you see. Equation 10 gets this form. Transform. So what is the term del? What is the del term? 30032. Are you there? Charvi J 30032. Carvi Jain, are you there? So this delta is basically the Dirac function. Okay, so this is our conclusion, you see. If you compare equation 9 and 11, we get delta t equal to d epsilon by dt. So whenever we are introducing a step change in error signal, particularly during that vertical change in error signal, the derivative action provides infinite quantity. So that is basically called derivative kick. I repeat, when you introduce a step change in error signal, during that vertical change in error, the derivative term provides infinite quantity. That corresponds to derivative kick. Okay, so you know derivative of any vertical line is what? Derivative of any vertical line is infinity. Is this clear?
Yes, sir.
Okay, so this is derivative kick. We'll come a little later how to tackle this situation. And this is a, a drawback, potential drawback, in fact, you can say, of the derivative action. So we'll discuss this issue a little later. Just before that, we want to discuss another observation, that is third one. Fine, you see this third comment. First you note down the third point, then we'll elaborate this issue. So did you see anywhere this type of figure? I mean, related to any chemical engineering problem? Student, did you see this type of figure, or it's better to say process response with time anywhere?
So when the valves are loose and it's shaky, so they give a noisy response.
Particularly if you go for industrial training and if you visit the control room for many processes, you can say almost for all processes, particularly in chemical industry, we have this type of response. Okay, and this response is basically because of the noise. Noise in the sense, suppose you are going to measure one product. You are going to measure one product purity, suppose. So there is certain, noise associated with the measurement instrument. I mean, if you measure the sample now, and if you measure the same sample after maybe few minutes, I'm sure that you will not get exactly same value. Little bit deviation will be there. This happens because of the measurement inaccuracy. Okay, and that is the source of this noise. So this inaccuracy may be associated with the instrument along with how we are handling. So these are basically called noise, and particularly it is called measurement noise. The instrument is not 100% accurate. The operator who is going to measure it using one instrument, that is also not accurately done. I am talking about 100% accuracy. So definitely there will be some deviation from time to time. And that's why it happens, So this is related to the noise. And this noise we usually cannot handle by employing one controller. That is what it is written here. See, for a noisy response with almost zero error means if you take average for a particular time instant, you will see that it is almost zero because there is some positive side. I mean, positive error, negative error, like that way. It may not be so systematic, but for a particular time duration, we can consider that this is, if you make the sum, it is coming to y set point only or y steady state value only. Okay, so for this, it is not recommended to employ any action through the derivative term. And in fact, you are understanding here, you see, this change is although not vertical, but it's close to vertical line. Only difference is that here there is one time duration involved. Okay. So it is close to vertical line. Now, if the derivative action is implemented, derivative action may take aggressive action because of this, which is not desirable. That is what mentioned here. Got this point? In fact, you can note down this para. It can better, explain this issue. You note down this para. it explains why we do not need any particularly derivative action against this noisy response. So these are happening, this gap or band, it may be plus minus 1%, plus minus 2%, plus minus 3%. These are due to the noise. These are not the process deviations. So there is no need to take any corrective action from the controller. Okay. Understood this point, student? You can ask me if you have any doubt. Okay, if not, we will go to the next remark. As I mentioned, we want to discuss how to tackle or how to reduce the effect of derivative kick. Our fourth remark deals with the issue that how we can reduce the effect of derivative kick. So you see the issue is explained in this way again. This is a transfer function of the PID controller. This is a transfer function of the PID controller that we derived a couple of minutes back. Now, if you remember, I told that the transfer function is basically the ratio of two polynomials. One is in the numerator and second one is in the denominator. And the order of the denominator must be higher than the order of, or at least equal to the order of the numerator. Otherwise, the system is improper. In fact, we have used another term, not physically realizable. Because if the order of the numerator is greater than the order of denominator, in that case we get infinite value and it's not physically implementable. And that's why additionally we have used another term that it is not physically realizable. I repeat, transfer function is basically the ratio of two polynomials. One is in the numerator, another one is in the denominator. So for proper, we must have the order of the denominator greater than the order of the numerator, or at least equal to. But in this case, it is not happening, and that's why it is improper. And for the case of improper, we have infinite value, and that we cannot physically implement through the instrument or valve. And that's why we have also used another term that is not physically realizable. Okay, so you are understanding why this tau ds is creating problem. So how we can make it proper? We just multiply one filter, capital F. To make it derivative term proper, we multiplied here one filter, you see F, and this F has this transfer function. N is the order of the filter. You have to decide depending on the numerator polynomial. Okay, but this is a condition. Order of tau ds must be less than or equal to n. To make it proper, we have just multiplied one filter with the derivative term, and filter transfer function is given here 1 by tau fs plus 1 whole to the power n. N is order of the filter. For this case, even we can consider 1 or 2. Fine. So this is all about the three control schemes. We have started with P only, PI and PID. So if you have any doubt, you can ask me now. Otherwise, we'll go to the next topic. Any doubt, student? If not, we'll go to the next topic. Yeah. This is our next topic. So previously we have discussed about the process, particularly open loop process. Next we have discussed about the controller. Now we want to discuss by joining both of them, process plus controller. And we want to investigate the dynamic response of this closed loop process. I repeat, initially we have discussed about different processes. Subsequently, we have discussed separately the three controllers, P, PI, PID. Now we want to connect them. Open loop process plus controller. So that is called closed loop process. And we want to discuss now what is the dynamic response of this closed loop process. Fine. In fact, the stability is also briefly discussed for open loop process. Now we will discuss for closed loop process. So let us come one by one. You see, this is our block diagram, which we have developed before. You draw this block diagram first, then we will discuss this. This is a block diagram which we developed before. I mean, we learned how to develop this block diagram. Now, first you draw this block diagram and then we will discuss further on this. So here GP is the transfer function of the process output Y with reference to M, manipulated variable. And GD is the transfer function of the process output Y with reference to D, disturbance variable. I repeat, GP is the transfer function between Y and M. M is manipulated variable. And GD is a separate transfer function of Y with reference to D. D is disturbance variable or load variable. Fine. So if you recall the classification table, variable classification table, there we had two types of input variables. One is manipulated variable, another one is disturbance variable. So this M is manipulated variable and D is disturbance variable. Okay. Now let us consider all these four elements one by one. Four elements means one is process, measuring device, controller, and final control element. Let us discuss all four individual elements: process, measuring device, controller, and final control element. Here I just want to add one thing. This controller adds not only this GC, this controller also adds this comparator. You remember this. Controller basically combines this GC control block along with this comparator. Both are programmed in the computers. Okay. Now let us come to the process. You see, I think we can write the process in this form. Equation 1. This is based on the concept output by input. So y equal to, we can write GP m bar plus GD d bar. Fine. Now let us come to write the measuring device. Here our output is ym, input is y, and transfer function is gm. So ym bar equal to gm y bar. Output by input equal to, straightforward way we can write equal to gm. Now come to the comparator. Comparator output is epsilon. And in the input side, there are two variables. One is set point and ym. Basically, it subtracts ym from set point value. Come to the controller. This is the controller equation. Here output is C, input is epsilon, and transfer function is GC. Then final control element. Again, final control element output is M and input is C. Transfer function is GF. Now you see how we will proceed. You see in equation 5, C is there. So we'll substitute equation 4 in place of C in equation 5. Follow me. We want to find the expression for M. So what is M? GFC bar. So GF is there. In place of C bar, we can substitute equation 4. Fine. Now we'll substitute equation 3 in place of epsilon. In the next phase, we will substitute equation 3 in place of epsilon. Then in place of ym, we will substitute equation 2. In place of ym, we are substituting equation 2. Now only equation 1 left. Can you tell me the final expression?
So GF GC YSP bar minus GF GC GM GD D bar whole divided by 1 plus GF GC GM GP.
See, you do like this way. You keep y in the left hand side. And in the right hand side, you just sum up two terms. One is associated with YSP plus something multiplied by D. I repeat, you get the final expression in this way. You keep Y in the left hand side. And in the right hand side, there are two terms. One is something multiplied by YSP plus something multiplied by D bar. Y equal to something multiplied by YSP plus something multiplied by D bar. You try to get in this form.
Sir, I was telling the final value of M bar. I substituted Y bar with GP M bar plus GDD bar.
Yeah, now you substitute in equation 1. We're talking about this one, no? M bar.
Yes, sir, yes.
You substitute in equation 1 and let me know the final expression. I repeat again, you get the final form in this way. Y equal to something multiplied by YSP plus something multiplied by D.
Sir, it is GPS GF of S GC of S multiplied by YSP minus GM of bar S plus GD of D bar S.
What is in the denominator?
Sir, I have not.
No, denominator will be there.
Sir, is it GF GC GP YSP bar plus GD D bar upon 1 plus GM GC GS?
One is missing just.
Yes, sir. 1 plus GM GC GF.
No,
In denominator.
one transfer function is missing. Just recheck.
Sir, in denominator it is 1 plus GF GC GM GP.
Yes. In denominator, you will get 1 plus multiplied by all 4 transfer functions. All 4 means not GD, excluding GD. Who told last the correct expression, denominator term?
Sir, 19CH 30008.
Yes. Anyone else got the expression?
Yes, sir.
Tell me, what is the denominator term only?
So 1 plus GP GF GC GM.
Yes. I think you can verify now. This is the expression. And this is called as closed loop transfer function. I have written CLTF. Okay, you note down this point because we'll use extensively this equation in our subsequent study. Closed loop transfer function, CLTF. Closed loop transfer function. We'll extensively use this equation in our subsequent study. So you remember all the times this equation. Okay, so the first term which is multiplied with YSP, that provides the effect of YSP on Y. And second term basically provides the effect of D on Y. What I want to mean, suppose there is a step change, then what will be Y? That we can investigate based on this first term. If there is any change in disturbance, then what effect it will have on Y? That we can get from the second term. Okay, in fact, we can separate like this way. You see, as I told, if we consider D equal to 0, then our closed loop transfer function becomes equation 7. Our closed loop transfer function becomes the terms which are represented in equation 7. Okay, So I am giving simply one example, or in fact you can note down this also. If you recall the distillation column, we had two product purities. One is at the top, distillate composition, and one is at the bottom, that is bottom composition. Suppose we are currently producing 95% purity. So our current YSP is 0.95. Now say after few days, as per the market demand, we need to increase the purity from 95 to 99. So how will change YSP? It will change from 95 to 99. Got the example? For any chemical process, if we consider the temperature or the product purity, currently what we have, in future we may want to get more than that or less than that as per the market demand. In that case, we can change this YSP and we can observe the process dynamics Y. Okay, this is one example. Now another one is regulatory problem. So in this problem, we basically consider set point equal to 0. But disturbance term remains there. This is called regulatory problem. Set point 0 and disturbance is there. An example is very simple. Again, if you consider that distillation column, we had the disturbance feed flow rate or feed composition, feed temperature, feed pressure, all these are disturbance. So if there is any change in any of these disturbance, in any of these disturbances, if there is any change, then what effect it will have on the product purity Y, that we can know from this equation. Okay. So I think we do not have more time to proceed further. Yeah. Any doubt, student? If you do not have any doubt, let's stop here. So thank you to everyone.
Thank you, sir.